early warning signals consisted of wood fires on a hill that faced seaward. Bales of pitch and oakum were also burned in open grates or fire baskets. Eventually, the fires were moved to the top of tall towers with open lantern rooms. Wood was a primary fuel for many centuries. By the 16th century, coal was introduced as an illuminant. Unfortunately, there was more smoke than fire. At the end of the 17th century, lighthouses consisted of closed lantern rooms with glass storm panes. 1-pound candles in chandelier settings were used as an illuminant. Despite their reliability, candles simply were not as bright as other illuminants. Oil lamps were soon to follow. Most lamps had solid rope wicks made of loosely braided cotton. The common wick channel lamp was probably one of the first style oil lamps to be used in lighthouses. Several wicks placed in channels around the perimeter of the lamp were fed from a common oil reservoir. This lamp was common in the early 1700s. The main disadvantage of this style lamp was the small reservoir. By the mid-1700s, the pan lamp replaced the common wick channel lamp in some lighthouses. The number of wicks varied from 2 to as many as 24. One advantage of the pan lamp was the visibility of all wicks from any direction. Also, the large reservoir held enough oil to allow for at least 12 hours of continuous operation. The bucket lamp was used in lighthouses in the late 1700s. This lamp had 2 to 4 spouts carrying a large diameter rope wick that extended into the body of the lamp. Below each spout was a similar shaped drip catcher. The large reservoir also held enough oil to burn for at least 12 hours. One disadvantage was the bucket blocked the flames on the far side when viewed from certain directions. The first major revolution in lighthouse illumination came in 1782. Argand, a Swiss-born physicist, invented a lamp with a hollow cylinder wick placed between 2 concentric brass tubes. Air was drawn up through the vents in the base of the lamp and allowed to pass through the center of the wick. Air also vented around the outside of the wick through holes in the base of the chimney holder. The oxygen allowed for a very intense and nearly smokeless flame. Later, a tapered chimney was placed over the flame, which focused air currents and intensified the light even more. Also in the 1700s, reflectors were being put into use in some lighthouses. One of the earliest parabolic reflectors consisted of a wooden bowl with small facets of silvered glass affixed to the interior with plaster. Metal reflectors were soon to follow. After the invention of the Argand lamp in 1782, parabolic reflectors were mounted behind the lamp. This combination was another major advancement in lighthouse illumination. The light that radiated back into the reflector was directed into a cylindrical beam. This system uses reflection for directing the light and is known as the Catadioptric system. There were some disadvantages. Only about 60% of the light was actually reflected. The rest absorbed into the surface of the metal. The light that radiated forward was simply lost as it spread in all directions. The reflectors were mounted on a metal framework also called a chandelier. The arrangement of the reflectors on the chandelier determined the characteristic of the light. Reflectors mounted evenly around the perimeter of a circular framework exhibited a fixed characteristic which could be seen at any point on the horizon. Reflectors positioned side by side and mounted in a faceted arrangement will exhibit a flashing characteristic as the chandelier rotates in the observer's line of sight. Reflectors did require a great deal of care and maintenance. Each reflector required polishing and housed a lamp, which needed oil and a wick to be trimmed. It wasn't uncommon to have as many as 28 reflectors on one chandelier. Reflectors remained the primary device for directing light seaward for over 50 years. In 1810, Winslow Lewis, a retired sea captain, patented a device he called a magnifying and reflecting lantern. He sold the rights to his invention to the U.S. government in 1812. Some said Lewis provided a great service to his country through his inventions. Others said he appropriated many of his inventions and produced shoddy lighthouse construction and equipment. His design included a lamp, a reflector, and a magnifier. The lamp was a crudely built version of an argon lamp. The reflector was a thin sheet of copper formed into a spherical shape. The magnifier was a cast plano-convex lens. It was semi-transparent because of its green color and poor quality. Early versions of the lens were 9 inches in diameter and 4 inches thick. The spherical-shaped reflector collected the light that radiated behind the lamp and sent it back through the light source. This intensified the light that radiated toward the lens. The light was then refracted into a beam after passing through the lens. In theory, Winslow's design was good. Unfortunately, the quality of the equipment was very poor. The lens was too thick, poorly shaped, and its dark green color made it nearly useless. Some lighthouses removed the lens hoping to improve the light. Since the reflector was spherical and not parabolic, the light was allowed to scatter, making a poor system even worse. Over the years, Winslow Lewis manufactured several sizes of reflectors, both spherical and parabolic. After numerous investigations, it was discovered that many of the parabolic reflectors were actually spherical. Even though his reflectors were of such questionable quality, they remained in U.S. lighthouses until the 1850s. Attempts were made as early as the mid-1700s to manufacture lenses for lighthouses. Some of these lenses were 21 inches in diameter and 5 inches thick. The glass used was very poor quality with many bubbles and impurities. These lenses were so thick and the quality of the glass was so poor, there were reports that they actually reduced the light. One of the main disadvantages of these early lenses was spherical aberration. The light rays that passed through the center of the lens exited horizontal as designed, but the light that passed through the lens near the edge exited at a steeper angle and could not be seen by the mariner at a distance. In 1748, Count Buffon proposed grinding a solid piece of glass into steps or rings, collapsing a simple spherical lens into concentric zones. This would greatly reduce the weight and thickness and the amount of light that was absorbed in the glass. Condorcet in 1788 and Sir David Brewster in 1811 suggested building these lenses from separate pieces consisting of stepped annular rings. None of these lenses were intended for lighthouse purposes, and most important, they were not designed to correct spherical aberration. In 1819, Augustin Fresnel, a French physicist, invented a lens system that would be one of the greatest advancements in lighthouse illumination. Unacquainted with the suggestions of Condorcet or Brewster, Fresnel designed and was the first to build an annular lens system that nearly eliminated spherical aberration. This is a photograph of one of Fresnel's early lenses. The first lens installed at Cordouan Lighthouse in 1823 consisted of 8 panels of annular lenses placed around a lamp at a focal distance of 920 millimeters. To collect the light that would otherwise escape above the lens, Fresnel placed a series of plain silvered mirrors on which the light was thrown by another system of lenses. Fresnel's design is based on refraction, or the bending of light through glass. Light that enters perpendicular or normal to the surface will not have its path altered. Light that enters the surface at an angle will slow down and refract as it enters the denser medium. It then speeds up and refracts as it exits the glass. If the surfaces are parallel to each other, the light is offset, but the angle of its path is unchanged. To change the direction of the light, the surface of the glass can be shaped to achieve the desired path. Fresnel used only a small section in the center of a large diameter spherical lens. This segment was the most accurate in focusing the light and had minimal spherical aberration. He then added concentric rings around the center of the lens, adjusting each face to correct for spherical aberration. The thickness of the assembly was less than 1.5 inches, reducing the weight and the amount of light absorbed in the glass. This lens assembly is termed the dioptric system, which means that the light is refracted twice, once as it enters and again as it exits the lens. Examining each segment in more detail, Fresnel used a formula for the center bullseye lens that calculated two independent radii and then averaged them together. Even this small lens segment exhibited some spherical aberration. To minimize this, one radius was calculated at the axis of the lens, the other calculated at the margin. The two radii were added together and divided by 2 to achieve an average radius with the smallest amount of aberration as possible. A series of zones were designed around the center lens to complete the dioptric assembly. Fresnel's formula for a dioptric zone calculated the radius of the outer face and the center location of that radius. The center lens is the only truly spherical part of Fresnel's bullseye design, with its center of curvature located on the focal axis of the lens. The center of curvature of each dioptric zone recedes from the axis. This is done to achieve a steeper angle on the face of each zone as its distance increases from the optical center, eliminating spherical aberration. The bending of light through a dioptric zone can be demonstrated by two refraction formulas. The angle of the incoming ray is measured perpendicular or normal to the surface of the glass. This zone has an incoming angle of 27.04 degrees. The index of refraction is a ratio of the density of air to glass. Crown glass has an index of 1.51. The sine of the incoming angle divided by the index of refraction equals the sine of the refracted angle. The refracted light as it passes into the glass is 17.52 degrees, also measured normal to the incoming surface. The exiting ray is calculated in a similar fashion. The angle of the internal ray, 27.74 degrees, is measured normal to the exiting face. The sine of this angle multiplied by the index of refraction is equal to the sine of the exiting ray. The exiting angle light ray is equal to 44.66 degrees, also measured normal to the exiting face. A properly designed dioptric zone will collect light from the lamp or focal point of the lens and refract the light through the glass exiting horizontal and directing it seaward. All calculations were derived from a single point of light that scatters in all directions. This allows the light to spread as it's refracted in the glass. If the outer face of the zone was flat, the light would also spread upon exiting. This is why it is necessary to have a curved outer face on each zone, focusing the light so all rays exit horizontal. The dioptric panel is located in the center of a Fresnel lens encompassing approximately 57 degrees from the focal point. Smaller sizes or orders of Fresnel lenses have fewer dioptric zones because of their shorter focal lengths, but they all encompass the same 57 degrees. Increasing this angle made it difficult to direct the light seaward using refraction only. To solve this problem, different style prisms were designed to use both refraction and reflection. The term catadioptric, meaning reflection, and dioptric, meaning refraction, were combined, and these prisms were termed catadioptric. They were placed above and below the dioptric panel to direct the light seaward. Fresnel's formulas calculated the angle of each refracting prism face along with the center of curvature and the radius of the reflecting surface. Light is allowed to pass through the surface of the glass only to a certain angle. If the angle is too steep, the light will no longer pass through the glass but will encounter total reflection. This is called the critical angle. This angle is calculated by the ratio of the index of refraction of air to glass. Crown glass has a critical angle of 41.5 degrees measured perpendicular to the surface. Any light reaching the surface at this or a greater angle will be reflected. The light will then travel through the exiting face, being refracted to the horizon. The light source at the focal point radiates in all directions, coming in contact with the prism at slightly different angles. The light then spreads as it is refracted through the first prism face. If the back face of the prism was flat, the light would also spread as it is reflected, and likewise as it is refracted while exiting the prism. To focus the light so all rays exit horizontal, the reflecting face of the prism is curved. The radius of curvature and the location of its center are calculated using Fresnel's formulas. The entrance and exit faces of the prism are also set at unique angles. The light that enters the very top corner of the prism will be refracted as it enters, reflected off the second face, and then travel parallel to the prism face before being refracted as it exits horizontal. Likewise, the light that enters the very bottom corner will be refracted and then travel parallel to the exiting face before being reflected and refracted to the horizon. The catadioptric prisms are also set into the brass frame at unique positions. The light that passes just over the upper corner of one prism will line up perfectly with the lower corner of the next prism. This arrangement captured the light that radiated out from the lamp, not allowing any light to escape between the prisms. They were also positioned with the exiting faces directly above one another, forming one solid sheet of light directed to the horizon. This section view of a Fresnel lens shows the arrangement of the dioptric lens assembly in the middle, with the catadioptric prisms above and below the lens. The lenses and prisms surround a lamp placed at the focal point. The lamp radiates light in all directions. Approximately 70% of the light is captured by the Fresnel lens assembly. The area at the top of the lens is reserved for the chimney and exhausting the lamp. The base of the lamp and the shadow it casts block the lower area. There were many improvements to Fresnel's original design over the years. The curved catadioptric or reflecting prisms mounted in a rotating light were not invented until 1849 by Thomas Stephenson and was first exhibited in 1851. Around the same time, J.T. Chance developed a spherical mirror that directed light back through the lamp, enhancing the intensity of the light. These glass prisms were far more efficient than the metal reflectors that were sometimes used. There were 4 original orders of Fresnel lenses corresponding to the focal distance and the number of concentric wicks in the lamp. The first order having a focal distance of 920 mm and a lamp with 4 concentric wicks. The second order having a focal distance of 700 mm and a lamp with 3 concentric wicks. The third order had 2 sizes with focal lengths of 500 mm and 250 mm, each having a lamp with 2 concentric wicks. The fourth order having a focal distance of 150 mm and a lamp with 1 wick. These sizes eventually changed to 6 orders. The first, second, and 500 mm third order remained the same. The 250 mm changed to a fourth order. The 187.5 mm was added and became the fifth order, and the 150 mm became the sixth order. In the mid-1800s, a small third order with a focal distance of 375 mm was added. In the 1880s, 2 larger lenses were added, a mesoradial with a focal distance of 1,125 mm and a hyperradial with a focal distance of 1,330 mm. The hyperradial was the largest lens ever built. Only one of these lenses was ever installed in the United States, in 1909 at the Makapu Point Lighthouse on the island of Oahu, Hawaii. There are 2 basic types of Fresnel lenses, fixed and rotating, and also a combination of the 2 called a fixed flashing lens. They all follow the same classic Fresnel cross-section. The difference is what axis the section is revolved around. A fixed lens has its profile revolved around a vertical axis located through the focal point, generating prisms parallel to the horizon. This design focuses the light vertically, but it is allowed to spread in the horizontal direction, forming a belt of light. A rotating lens has its profile revolved around a horizontal axis located through the focal point. This creates concentric rings, which focuses the light into a cylindrical beam. The fixed lens is segmented into a number of belt lenses and reflecting prism panels arrayed 360 degrees and mounted in a brass framework. This entire assembly rests on a stationary pedestal. From a distance, a fixed lens displays a continuous glow that can be seen at any point on the horizon. The rotating lens is segmented into a series of flash panels arrayed around the focal point. Each flash panel consists of a center bullseye lens with reflecting prisms above and below the lens. The entire lens is mounted on a rotating pedestal. Before electricity, these massive lenses were rotated by a clockwork mechanism similar to the concept of a grandfather clock. A weight would drop down the center shaft of the lighthouse attached to a cable, which was wound to a drum. The drum was linked to a series of gears. The ratio of the gears were designed to allow the weight to drop at a certain speed. A governor was also provided for fine speed adjustments. A pinion gear from the clockwork would interface with the large ring gear attached to the pedestal. Carriage wheels, ball bearings, or mercury baths were used as a means of rotation. This first-order lens has 8 flash panels with a total of 368 individual pieces of glass, and stands 9 feet tall. The entire assembly is 17 feet tall when mounted to the rotating pedestal. From a distance, the lens creates a flash as one of the panels rotates in your line of sight. In between the panels, there is no light directed toward the observer, creating an eclipse. The number of flash panels and the speed at which the lens rotates determines the characteristic or signature of the lens. There are many combinations of the two basic fixed and rotating lenses. This lens contains a fixed or belt lens segment noted by its horizontal prisms, flanked by 2 rotating or bullseye-style lenses. The reflecting prisms above and below the center belt are also fixed horizontal prisms. This is called a fixed flashing lens. From a distance, the characteristic of a fixed flashing lens is a continuous glow, usually produced from horizontal reflecting prisms, with a series of flashes produced by bullseye lenses. There are a number of style lenses that produce a fixed flashing characteristic. The fixed lens is not as bright as a rotating lens because of the way it distributes the light. The lens spreads the light 360 degrees to all points on the horizon. There is only a small band of light that is visible to the observer at a distance. The remaining light outside of this band is distributed to either side of the observer. A rotating lens displays a pattern of light the same width as the flash panel. The wider the flash panel, the more light that is directed toward the observer. For this reason, one of the most efficient and powerful lenses is the bivalve, also known as a clamshell lens. Nearly 50% of the light from the lamp is collected in each flash panel and focused into a beam. Another important factor in the range and power of the lens is divergence. Fresnel's formulas were all derived from a single focal point. But in reality, there is no light source that is as infinitely small as a point. The flame height in most lamps averaged 2 to 3 inches. Light radiating out from the top of the flame would enter the prism at slightly different angles than was calculated. The result was an exiting light ray that was not horizontal. This effect, called divergence, is the reason why the beam has a slight spread as it exits the lens. Divergence was actually an advantage to the Fresnel lens. If all the rays exited horizontal and the beam was a perfect cylinder, the observer would only see the light at a specific point on the horizon. The diverging rays made the lens more forgiving, sending the light out to a wider range on the horizon. The range of a Fresnel lens is determined by a number of factors including atmospheric condition, the order of the lens, and the height of the lens above sea level. In good atmospheric conditions, the only limiting factor for the more powerful Fresnel lenses is an obstruction from the curvature of the Earth. Early formulas show how the range was calculated using the focal plane height of the tower above sea level, the observer's position above sea level standing on the deck of a ship, and the radius of the surface of the Earth. The lantern room housed the Fresnel lens and protected it from the elements. There were 4 different size lanterns designed for first, second, third, and fourth order lenses. The ventilation in the lantern was critical for proper operation. Each lantern contained ventilators at floor level, allowing fresh air to enter and pass through the lantern, exiting out the vent ball mounted in the roof. This kept the room cool in the summer months, provided oxygen for the lamp, and also prevented condensation from forming on the lantern room windows. There were various fuels and lamps that evolved over the years. Some of the earliest fuels used were various fish oils. Around 1800, sperm whale oil, also known as spermaceti, was the fuel of choice. In the 1840s, the Industrial Revolution caused the price of whale oil to skyrocket. Experimentation began with alternative fuels. Some of these included olive oil, peanut oil, coconut oil, lard oil, and colza, also known as rapeseed oil. Colza, which was produced from the seed of wild cabbage, proved to be the most advantageous, producing light equal in quality to that of whale oil at approximately 1/2 the cost. Around 1870, kerosene, also known as earth oil or mineral oil, costing a mere fraction of the expensive animal and vegetable oils, revolutionized the illumination of lighthouses. As early as 1858, Trinity House, in charge of British lighthouses, employed electricity installing a carbon arc lamp in the South Foreland Light Station. The first lighthouse to use electricity in America was the Statue of Liberty in 1886. Several styles of lamps were used inside Fresnel lenses. Capillary lamps are based on the principle of capillary action, drawing fuel up the wick from a reservoir mounted below the burner. These lamps were used in 4th, 5th, and 6th order lenses. Constant level lamps used gravity with the reservoir mounted above the lamp, allowing the oil to flow down a tube to the base of the lamp. An adjustable air vent was placed in the reservoir to produce a constant flow of fuel to the lamp. Mechanical lamps employed the use of a clockwork or mechanical device to pump oil to the lamp. Typically, 5th and 6th order lenses use lamps with 1 hollow wick. 3rd and 4th order lenses use lamps with 2 concentric wicks. 2nd order lenses used 3 concentric wicks, and 1st order lenses used 4 concentric wicks. Later, lamps with 5 concentric wicks were designed. One problem encountered with early multiple wick lamps was the melting of the solder in the burner due to the intense heat. In 1819, Augustin Fresnel and Francis Arago designed a lamp that employed the use of a clockwork mechanism that would pump oil to the burner at a rate much higher than could be burned. The oil would overflow the wicks, cooling the entire burner. In the late 1830s and early 1840s, 2 styles of moderator lamps were designed, one using a spiral spring, the other a weighted piston to push oil up to the wicks. Pneumatic and hydraulic lamps were also used in Fresnel lenses. The pneumatic lamp used air pressure, and the hydraulic lamp used fluid pressure to force oil up to the burner. In 1853, Lieutenant George Meade designed a hydraulic lamp intended to replace the French mechanical lamps. His design consisted of an oil reservoir mounted in the dome of the lantern room, forcing oil to the burners by the pressure generated by gravity due to the height of the reservoir above the burner. In 1853, Joseph Funk, the foreman of the lamp shop at the New York depot, designed the hydraulic float lamp. The oil would flow through the chamber containing a float that was adjusted to open and close a valve in the oil inlet when the oil reached a proper height in the wick reservoir. This maintained a constant oil level. In 1868, American ship captain Henry Doughty designed a lamp that burned the newest fuel, kerosene, In 1876, Joseph Funk designed his own version of a kerosene burner that was eventually used by the Lighthouse Board. In the late 1800s and early 1900s, various styles of incandescent oil vapor lamps were invented. These lamps use air pressure to spray kerosene mixed with air into a heated vaporized chamber to form a volatile gas that soaked into a mantle, producing a light 3 times as bright as Argand-style lamps previously used. This design is similar to today's Coleman lantern. Electricity was available in lighthouses as early as the 1850s. The first electric lamps used in lighthouses were electric arc lamps and were installed in some lighthouses as early as the 1860s. An electric current was supplied between 2 carbon rods spaced a certain distance apart, allowing the current to jump between the rods, producing an intense light. Early incandescent light bulbs were unreliable and were not put into use until after Thomas Edison invented the tungsten filament light bulb. Bulbs of 1,000 to 3,000 watts replaced arc lights in many lighthouses in the early 1900s. Halogen 500 and 1,000 watt bulbs are used in today's classic Fresnel lenses. There were several companies that produced Fresnel lenses in Europe. This is a list of the major manufacturers, most located in Paris, where Fresnel lens construction began. The Chance brothers from England began production around 1850. One American manufacturer, Macbeth Evans, produced Fresnel lenses in the early 1900s. 2 types of glass were used in Fresnel lenses, crown glass and flint glass. Augustin Fresnel chose crown glass in his early lenses because it produced fewer striations during the casting process. Also, crown glass did not contain lead, which made it lighter than flint glass. This was a major advantage considering the amount of glass contained in the larger order lenses. One disadvantage was the green color that existed in crown glass. Arsenic was added to some formulas to reduce the color. Crown glass was used by European manufacturers until the late 1800s, when the Chance brothers from England began experimenting with flint glass. Flint glass had a higher index of refraction of 1.58 as compared to crown glass with an index of 1.51. This meant the light was bent at a steeper angle passing through the flint glass. It was also less prone to bubbles during the casting process. It contained lead and was nearly colorless. Macbeth Evans, the only American manufacturer of Fresnel lenses, used only flint glass in their lenses. They made 4th, 5th, and 6th order lenses from 1912 to 1930. The Fresnel lens was the most revolutionary advancement in lighthouse illumination. They have guided mariners for over 150 years. Many lighthouses still retain their classic Fresnel lenses. Many are on display in museum exhibits. Modern lenses in lighthouses today, along with automobile taillights and stage lighting, are manufactured using the same design concept Augustin Fresnel used in the early 1800s. Lighthouse organizations all over the country are making efforts to restore and maintain classic Fresnel lenses. This magnificent lens can best be described by Alan Stevenson, a distinguished lighthouse engineer who wrote, "Nothing can be more beautiful than an entire apparatus for a fixed light of the first order. It contains the central belt of refractors forming a hollow cylinder 6 feet in diameter and 30 inches high. Below it are 6 triangular rings of glass ranged in a cylindrical form, and above a crown of 13 rings of glass, forming by their union a hollow cage, composed of polished glass 10 feet high and 6 feet in diameter. I know of no work of art more beautiful or more creditable to the boldness, intelligence, and zeal of the artist."